Welcome to my YouTube channel Mechanical Engineering Management, and this is the machine design lecture series. So today we are going to discuss about the chapter Design Against Fluctuating Load, in which this is the specific point factors affecting endurance limit. So this is very important question. Previously we have discussed about the endurance limit. So now it's turn for the factors affecting on this endurance limit. So let's see first of all the question that can be asked in your examination. Discuss the different factors affecting endurance limit. So the endurance limit of a material is not a fixed property. It is actually influenced by many of the parameters. It can be internal parameter or it can be external parameters. Internal parameter, that means material related, and external parameter, that means geometric or environmental factors. The following different factors, or you can say parameters, affecting endurance limit, and that you should remember: surface finish, then size effect, then type of loading, then temperature, then residual stresses, then stress concentration, corrosion and environment, next mean stress effect, and last one, material properties. So these are the different parameters, or you can say factors, affecting endurance limit. Now let's see one by one briefly, means very short. We are going to discuss about these different parameters. So let's start from the first one, surface finish. So here you can see this is the high precision shaft and this is the machine shaft. That means having some little bit scratches on the surface. So rough surfaces contain scratches, tool marks and irregularities, and that act as stress razors, and so that these increase localized stress concentration and hence reduce endurance limit. So specifically for the machine shaft having less endurance limit. Now this is the case. A smooth and polished surface, here you can see, having high endurance limit. So here you can see a ground steel shaft has higher endurance limit than a machine one. Second one, size effect. Generally, the larger components are more likely to contain micro defects like this one. These are the different micro defects like voids, inclusions, cracks. Here you can see. Here also you can see micro cracks. So in bigger parts, the probability of weak spot is higher because of having larger surface, and so that endurance limit will decrease. Now if you will talk about the smaller specimens that will be generally used in the tested labs, usually having higher endurance strength compared to full size machine parts. So if the smaller part, the higher endurance limit; if there is a larger components, less endurance limit. Now the third one, type of loading. Generally endurance limit varies with the mode of stress application. Here you can see these are the different mode of stress application. Generally axial loading, here you can see this is the axial loading, both are. It can be compression or it can be tension, having less endurance limit. So generally you can say lowest endurance limit. For the bending, here you can see having higher endurance limit, since stresses are localized at the surface only. Now the third one, torsion. Here you can see slightly lower than bending but higher than axial. So in the torsion case, the endurance limit will be lower than bending and higher than axial loading. In this diagram you can see this triangle represent as rotating or bending, so having higher endurance limit, and this square represent as axial load, means push and pull, or you can say tensile and compressive, having less endurance limit. Now fourth one, temperature. Higher temperature reduces the endurance limit because material strength decreases as temperature increases, and so that oxidation may occur. So very simple, if there will be high temperature, then endurance limit will decrease. Vice versa, if there is a low temperature, definitely it will improve the endurance limit. Now the fifth one, residual stresses. So in this figure you can see, if there is a compressive residual stresses, like from the process of short spinning, here you can see short pinning, carburizing, cold working, there will be delay in crack initiation because there will be compressive residual stresses, and so that it will improve endurance limit. But exactly in opposite direction, if there is a tensile residual stresses, that will accelerate crack growth, and so that it will reduce endurance limit. So very simple, if there is a compressive residual stress, more endurance limit. If there is a tensile residual stress, less endurance limit. Now the sixth one, stress concentration. Very simple, you can see for the keyway slot there will be stress concentration for that particular cross section of the shaft, and due to that there will be more stress concentration, that is called as stress risers, and these cause local stress to exceed average stress and hence reduce endurance limit significantly. Using the flat, smooth transitions and notch relief improve endurance strength. Now the seventh one, corrosion and environment. Here in this figure you can understand how it will affect on the endurance limit. So corrosive environments, mostly moisture, chemical, salt water, accelerate crack initiation and growth, and this leads to corrosion fatigue, drastically reducing endurance limit. So very simple, corrosive environments drastically reduce endurance limit. So to protect this corrosion, we have to use the protective coatings, lubrication or corrosion resistance alloy. Now the eighth one, mean stress effect. So here you can see this is the mean line for the stress. Here the mean stress is 0, and in these both cases the mean stress having some specific value. So endurance limit is usually measured for fully reversed loading, because of in case of mean stress 0, it is called as the fully reversible stress, and in that particular case the stress value is vary from the tensile to compressive, or you can say from the positive to negative, and that will be more dangerous for the machine component or parts. So if a mean tensile stress is present, fatigue life reduces, and this is corrected using Goodman, Soderberg or Gerber diagrams. Now the last one, material properties. So materials with higher tensile strength generally have higher endurance limit. Ferrous alloys like steel shows a true endurance limit. Here you can see the steel having true, or you can say unique or distinct endurance limit. And for the non-ferrous alloys like aluminium, copper, having no distinct value for the endurance limit. And here you can see this is the summary for the different parameters, or you can say different factors affecting on the endurance limit. So this is a very simple diagram, and from that you can summarize all parameters or factors affecting on the endurance limit. Thanks my dear friends for watching this video. Press the like button and share and subscribe this YouTube channel.